Alright, it's been like 2 hours since I started recording this one video. This is going to be the last take. I do not care. Alright, so sampling distribution is what happens when you map results. Okay, so sampling distribution is basically take a sample, right? So let's say you toss a coin 20 times. Okay? Now, of those 20 coin tosses, how many times did you get heads? Right? Let's say the first time you got 7 heads. Okay? And then you do it a second time, right? So you toss a coin another 20 times. Let's say this time you get 12 heads, and so on, right? Now let's say you did this experiment of 20 coin tosses 10,000 times, okay? You'll get a graph that looks a little bit like this, right? Okay, now this graph shows you how many times we got heads from 20 coin tosses, okay? And so you'll notice most of the time it's around 10, right? So most of the time you get roughly around 9 to 12 coin tosses, 9 to 12 heads out of 20 coin tosses, okay? Now obviously here we're assuming you did the experiment roughly 10,000 times, which is very impractical unless you're a computer, but I don't care. Right, so for sampling distribution of the mean is very similar to this, right? Now, this experiment with the coin tosses, a coin toss is has a binomial distribution, right? It's either going to be heads or tails. But with the sampling distribution of the mean, it's not binomial, okay? So instead, you're actually taking a continuous variable and you're looking at the full continuous variable, right? Compared to the number of successes, okay? So you're going to take the mean of a sample, right? So let me give an example to illustrate this, right? Let's say you took 3 patients, and you measured their blood pressure, right? And so, for example, the first one had a blood pressure of 105, second one had a blood pressure of 110, third one might have had a blood pressure of 115. Okay, so you averaged it out, okay, and you got the mean, right? So for this one, 105 plus 110 plus 115 divided by 3, you get 110, okay? Right, and so you take that 110, so that 110 is your mean, right? And let's say you took 10,000 samples, each of those samples have 3 patients inside them. And so what you'll end up with is 10,000 means, right? Each of those taken from a sample that has 3 patients. You took those 3 patients, you measured their blood pressure, found the mean of that sample. And then what you'll end up with is a graph that looks a bit like this, right? This one here, right? So you'll notice that most of the time we get a mean that's roughly close to the population mean, right? And so that's where most of the sample means are going to lie. One thing that's worth noting is that this distribution is narrower than the population distribution. And it's actually shown much better with this bottom distribution curve, where instead of taking a sample of 3 patients, we took a sample of 20 patients and we plotted their distribution. And so it's actually much, much narrower than the distribution of the population. Okay? But let's say the distribution of the population wasn't normal, right? Obviously this population has normal distribution, and so let's say it wasn't a normal distribution for a population, right? Let's say it was like this, right, where each of the values is equally likely. Well, when you start to take samples and you start to take the means of those samples, right, you'll find that it ends up getting turned into a normal distribution anyways. Okay, now why does this happen? Let's say that this represents the results from rolling a dice, right? So with the dice you can get 1, 2, 3, 4, 5, or 6, okay? And they're all equally likely, right? Now, if you roll the dice 3 times, you're probably not going to get all 3 rolls to be 1, or all 3 rolls to be 6, okay, you're probably going to get a mix of 3 different numbers. And when you find the mean of those 3 different numbers, it's probably going to be closer to the mean than if you'd had only one roll and you plotted out each of those rolls. Right, so with one roll, each one is equally likely, so you'll get an equal frequency of each. Okay? But with means, because the other values because the higher values will balance out the lower values, and so it will push the mean towards the middle. Okay? And again, the higher the sample size, the narrower the distribution. Right? And the closer it gets to a normal distribution. And again, with a skewed sample, the same thing happens. Higher sample size, more narrow. Higher sample size, more narrow, and closer it gets to normal distribution. Right? Now, one thing that's very, very important to note is that when we look at this graph here, let's say we drew down the mean for this graph. Okay, now for this graph, the standard deviation is, let's say here, right, standard deviation of 1. Let's say it's here. Okay, now if we tried to draw the standard deviation for this curve, it's not going to be at the exact same point as the standard deviation for the population, right? Because this curve is narrower, and so the standard deviation is also going to be narrower, right? And so rather than finding the standard deviation for this curve, which can be pretty annoying to do, you can just convert the population standard deviation into the standard deviation for the samples, right? And this is called the standard error of the mean, right? This converted standard deviation. And how do you convert the standard deviation for the population into the standard error of the mean, which is the standard deviation for samples? Is you take the standard deviation of the population here, and then you divide that by the sample size, okay? And the reason you divide it by the sample size is that the bigger the sample, the narrower the distribution, okay? And so the smaller the standard error of the mean is going to be. Okay, sorry, standard error of the mean is going to be smaller. Right, so you'll notice that for a sample size of 20, the graph is much narrower. The standard error of the mean is going to be narrower, so that we keep it at the same as the standard. So we keep it at the standard deviation, right? So basically, the standard error of the mean is just a standard deviation, but for sample means rather than for a population. And so this is a calculation just to find the standard error of the mean. So we start with the variance, and then we divide that by the sample size. After that, we take the square root to convert variance into standard deviation, right? And if you know the standard deviation of the population, you can replace this standard deviation with the population standard deviation. You don't actually have to know all of this calculation. All that you need to keep in mind is that standard error of the mean is the population standard deviation divided by the square root of the sample size, right? So why are we trying to do this? Why are we trying to make a distribution normal and then create another standard deviation for it, right? Well, it's because curves like this one, and this curve are very hard to work with when we want to find z values and probabilities, okay? It's a lot easier to work with a normal distribution. It's a lot easier to work with a normal distribution than it is to work with a skewed distribution, okay? And the second reason why is that it's very impractical to get the entire population, right? So what you'll do is you'll just take samples from the population instead, and then you'll just assume that it's normal distribution because it almost is, right? It's very close to a normal distribution, so you can just pretend that it's a normal distribution. right? And so once it is a normal distribution, you can find the z value for a sampling distribution, just like you can find it for. So yeah. So once you have a sampling distribution that looks a lot like a normal distribution, you can find its z values for each of the points, right? And you can also find the probability of getting values that are higher here, right? And so the probability of getting a value that's, say, this far away from the mean or higher is the p-value of an experiment, right? So that's the statistical significance. Okay? Okay. So I'm just going to go over this example here. Clean up. Right, so we have a population. We have a population here, and its mean is 105, right? So I'm just going to make a note of that. So I'm just going to make a note of that. So we have a population mean of 105, right? And then we have a population standard deviation of 10, okay? So let's say we took a sample of 16 patients, okay? So that means we have an N of 16, okay? And we gave them heroin, right? And we wanted to find out, does heroin lower blood pressure, right? And so we measured their blood pressure after giving them heroin, and we found out that their mean blood pressure was 100, okay? So that means that the mean of the sample is 100. Let me just write this thing down. I have been at this for hours. So we need to find out, is this sample mean statistically significant, right? Is the probability of getting a sample mean that's this far away from the population mean less than 5%? Okay, so the first step is to find the standard error of the mean. Okay, now as we explained, to find the standard error of the mean, you take the population standard deviation, so that's going to be 10, and then you divide that by the square root of your sample size, so that's 16. Okay, and so as you can see here, if you put this into a calculator, the result that you're going to get is 2.5. All right, and so that gives us a standard error of the mean of 2.5. I'm just going to write that down here. Okay. Right, and then the next step is to find your z value. Okay, so to take a z value. So to find the z value, you're going to take your population, you're going to take your sample mean, right, minus population mean, okay, and then you're going to divide that by your standard deviation, right? Now, because we're taking a sample here, right, we're going to work with sampling distribution. And remember, a sampling distribution has a narrower standard deviation than the population standard deviation. And the sampling distribution standard deviation is the standard error of the mean. And so in this case, it's 2.5. And so if you put this number into a calculator, you're going to get -2. Okay? So our z value is -2. Right? And for now, we're going to ignore the minus sign, but we'll get back to it in a bit. So now that we have the z value, we're going to look into a z table, okay? And we're going to look up the value for a z value of 2. And that gives us a value of 0.023. Right, now what this means is, on the graph, is that if we look at the graph here, for the sampling distribution, so this is our population mean of 105, this is our sample mean of 100, the probability of getting 100 or lower is 0.023, right? Is 0.023. Okay? Now, why are we looking at it lower and not higher, the way you do other examples? And the short explanation for that is, if I'm just going to go over here, is that if we draw a graph, right, and let's say so let's say we were finding the probability of getting a result that's this far from the mean or higher, right? This result would be p. Okay, so this would be p, and this result would be 1 minus p, right? So that's this. But because our z value had a negative sign, what we can do is we can drop the negative sign and now flip these two results. Okay, so now our z value, when we look at the z table, it'll give us the probability of getting a value that's this much, that's at this point or lower, right? Which is more useful in this case, because we won't have a z value that's negative. Okay? And so what we'd end up doing, and when we look at the z table and we get 1 minus p, what this gives us is this small gap over here, because it's lower, and we're looking at 1 minus p now instead of p, which would be higher. Okay? And so to find the probability that it's... Okay, so this number gives us the probability of getting this value or lower. Alright? But we want to know what's the probability of getting a value that's this far from the mean, or further away. And so what we need to do is we need to look at the opposite side of the graph, right? Because this number over here is equally far from the mean, it's just on the other side, right? And because it's a normal distribution and the graph is symmetrical, to find the probability of getting a value that's further away, that's this far from the mean, or further, sorry, I'm making a mess. So to get a probability of getting a value that's this far from the mean or further, all we have to do is take this probability and multiply it by 2. So that gives us 0.046 or 4.6%, which is our p-value. So this is our p-value, which is over here, right? So just to recap, why do we multiply it by 2? So when we first found the z value and we looked at it in the table, it gave us the probability of getting this part of the graph over here, right? Of getting a sample mean of 100 or lower, okay? But we need to find the probability of getting a value that's this extreme. So we need to find the probability of getting a value that's this far away from the mean, okay? And it could be lower or higher, alright? So we need to find both sides of the graph, okay? And now, because we got 4.6, okay, and 4.6 is less than 5%, we can say that it's statistically significant. Alright? And that's the first rule for statistical tests. Alright? So the first rule is that if you have a p-value, right? So if you did this check and you did it on both sides, and the final result was less than 5%, then you can say that your experiment was statistically significant. And if it is statistically significant, then you can reject the null hypothesis. And in this case, you can say that yes, the heroin that we gave the patient did in fact lower their blood pressure, and it wasn't just due to random chance. Alright? And when we do this, we have three assumptions that we're making. The first assumption is that we know the population mean and standard deviation. Right? And the second one is that the distribution is normal. Right? Now, because we're working with sampling distributions, and we converted a sampling distribution into normal, since we're working with sampling distributions and this made it normal, that way we know for a fact that the sampling distribution is almost normal, and so we can just assume that it's normal, right? So just to give one last example, right? If you take a sample of 16 people, so here's 16, what's the probability that the mean of the sample? Oh yeah, so if you take samples of 16, how many of them will have a mean lower than 108? Okay, so we're going to find a mean of 108. Okay, so we need to find the probability of getting 108 or lower. What does this look like on the graph? Here's 105, here's 108. We're trying to find this part of the graph. Okay? And so first of all, okay, we're going to find this part of the graph. That's step one. Okay? And so what we do is we start by finding the standard error of the mean. Now because this example is actually building off of the previous example, we can just take the mean, the population mean, and standard deviation from that. Okay? And so to find the standard error of the mean, just to recap, you take the population standard deviation and you divide it by the square root of the sample size. So 10 divided by square root of 16, that's going to be 2.5. Okay? And then to find the z value for a sample mean of 108, you take 108 minus 105 divided by 2.5. Okay? And if you put this into a calculator, you'll get a z value of 1.2. Right? Now, you'll notice there's no minus here. Okay? So I'm just going to put this in the graph. There's no minus. So what this means is we are actually finding the value of p here instead of 1 minus p. Alright? And so we then go to the z table, okay, and we check for the value of z value of 1.2. So 1.2 in the z table gives you a probability of 0.115. Okay? And then if you want to find 1 minus p, which is what we're looking for, yeah, you take 1 minus this probability. So 1 minus 0.115, which is going to give you 0.885. And that's our answer. So that's our answer there. Okay? And just to show you the graph, that's what this looks like. Okay, so first, we went and looked for the z value of getting 108, which is equal to 1.2. Okay? And again, that's how many standard deviations 108 is from 105. And so then we found the probability of getting a value of 108 or higher, okay, which we found from the z table to be a 0.115. And then the final step to get this, which is our 1 minus p, we just take 1 and we do 1 minus 0.115, and it gives you 0.885. And that's it. Please get me out of here, I'm done.